predicting a value, it's represented using a hat. Otherwise, it's given. This is predicted value. This is the actual value. Whenever you have predicted values, it's hat. Whenever you have a predicted value of beta naught, it's beta naught hat. Okay. So line is the assumption. Whenever you build a model, it is not something that you have built a model, job done, wash your hands, go home. Even before you run that model, even before you finalize the model, you need to ensure that the model assumptions are satisfied. And line is a model assumption. L stands for linear, I for independent, N for normal, and E for equal variance. Linearity, you know how to find out linearity in the various parameters using scatter diagram. You can do that. Okay, Sushant has done that research. SP in previous example stands for top speed of the car. Thanks for that, Sushant. Okay, so that means these coefficient values should enter linearly into the equation. I can put a square here. It will become quadratic. But what I'm interested in is whether these coefficient values or parameters or estimates, are they entering linearly into the model? Of course, scatter diagram is the best bet for that. Second thing is assumptions about the errors. Error is what? Predicted value minus actual value. Your error should be independent and identically distributed. If you take average of all your errors, it should be 0. If you calculate the variance, it should be constant. And if the variance is constant, it is called as homoscedasticity. That means there's no problem. However, if there is no constant variance, it is a problem of heteroscedasticity. And one more thing is, these errors should be independent of each other. Errors should be independent of each other. If they are not independent, then there's a problem called as autocorrelation problem. Guys, spend a lot of time on this slide and this recording. Go through at least 20 times if you do not understand. This is heart of your uh, entire data analytics. Okay, because majority of the times you will have continuous output and then you use linear regression. And assumptions about the predictors. Predictors are what? Inputs. They should be non-random, meaning you should have determined your historical data upfront. Non-random means historical data is decided upfront. You have the data with you. And measured without error, we are assuming that there is no data entry error, or the measurement system is reliable when you have collected the data of inputs. These inputs should be linearly independent of each other. If they are not independent of each other, there is a collinearity problem. Here we are discussing about independent inputs. Here we are discussing about independent error values. And finally, all of your observations should be equally reliable. So all the entries that you have should be equally reliable. It should not so happen that, hey, I'm giving you 81 rows. Out of these 40 rows, I'm 100% sure it's correct. Another 41 rows, I'm not so confident. Gone. Right? Each and every observation should be equally reliable. Okay. Now, let us try to solve this using the R code. There is something called as plot. Plot does variety of things. Plot in some sense will give you, in some scenarios, plot would give you box plot. plot would give you, in some scenarios, a box plot. In some scenarios, it would give you a line plot. In some scenarios, or in regression scenarios, you'll get this. Look, let us look into this. This is the first entry. Um, these are the residuals. Residuals or errors mean the same. Errors versus fitted values. As in how your predicted values increase, your errors should not increase or decrease. Your errors should remain constant. Remember, errors should be having constant variance, so on and so forth. Right? So errors should be constant. So it's more or less constant, this red line, right? It's more or less constant. There is no weird representation. If this red line would have been in this way, in this way, this red line, or if it would have been like that, that means we know for a fact that as and how your fitted values or predicted values increase, your errors are increasing. If it was in this way, if it was in this way, as and how your fitted or predicted values increase, your errors are reducing. So this is fine. Now you need to keep pressing enter, enter. This is called as normal QQ plot, quantile plot. This is used to check whether your errors are normally distributed or not. If all these data points fall along this line, majority of the data points are falling along this line, right? Hence you can say that errors are normally distributed. Here we have errors, residuals are errors. But one key thing that you notice here is 77 and 71. Just remember those, don't worry about those now. Okay, did anyone leave? Oh, Vishal has gone offline. Huh. Now let me enter. I'm also standardizing the errors. I think I have to also explain what is standardization. So I'm standardizing errors for now. Just remember that I'm making it unitless. When we standardize, we are making it unitless. I think yesterday I've discussed during PC, I believe. Standardizing means making values unitless, because volume has one unit, horsepower has a different unit, top speed of the car has a different unit, right? And then weight has a different unit. Hence I'm standardizing and then checking. Here also you have a straight line. That means there is no uh, a trend as such in the data. You have there is no trend in the errors basically. And finally the last plot, which is called as Cook's distance. Remember from the Cook's distance perspective that if this Cook's distance value is greater than 0.5, that means that observation is influential observation. Assignment for you all. What is the difference between influential observation and outlier? What is the difference between influential observation and outlier? So if you see here, there is one value which is falling beyond 1. So anything greater than 0.5 is influential observation. So 77 is influential observation.